Welcome to GeoMapApp Tours. This is Dr. Dwayne Rieger. Today we're looking at ocean sediments. We're going to look at the distribution of different types of sediments. We're going to look at the sorting of sediments, especially neritic sediments. And finally we're going to look at some images of sediments on the sea floor. So first, let's look at the distribution of sediments on the sea floor. Alright, so we have all these different colors which represent different types of sediments. So let's zoom in here. Alright, so what will help is if I pull up this legend which tells us what the colors indicate. So this is siliciclastic. This is so a mixture of terrigenous sediment with siliceous ooze. Volcaniclastic is from volcanic eruptions. Transitional, this is also finer grained terrigenous sediment mixed in with siliceous ooze. Then we have the pure biogenic or biogenous sediments, calcareous ooze, the radiolarian and diatom ooze. These are both siliceous oozes. Okay, and then we just have shell fragments and mixed calcareous siliceous oozes. So it's like a transition. So we see a lot of this light blue, right? A lot of this light blue. And what is this light blue? This light blue is calcareous ooze. Okay, so we see a lot of calcareous ooze. Also see a lot of this brown, and these are the clays, these deep sea clays. We don't see a lot of sand in the open ocean, right? Because that's larger in size, and so it settles out closer to the continents. So we see the gray. We zoom in. See more of the grays and the yellows and the oranges near the land, okay, because those are the coarser sediments that settle out close to land. And the finer clays are further away on the deep sea floor, okay, because the small particles can be transported further distances before settling. So we have a lot of fine-grained calcareous sediment and calcareous ooze. Those are the light and dark blues. So you see that a large portion of the sea floor is covered by calcareous ooze or deep sea clays. So that's what most of the deep sea floor is covered with. But if we go further south, the deep sea. As we go further south, we see that the blues stop and these greens pick up. So these greens, these are these siliceous oozes. And why there's no calcareous ooze down here, and why it's all siliceous ooze, because in these Antarctic waters, the water's too cold for calcareous ooze. Because the water's cooler, it has more dissolved CO2 in it. Because it has more dissolved CO2 in it, it has more carbonic acid in it. Because it has more carbonic acid in it, it's more acidic. Because it's more acidic, CO2 dissolves in the water, where the siliceous ooze does not. So siliceous ooze dominates in these cooler Antarctic waters. And as we go further north, we see the calcareous ooze once again disappears. We don't see the pickup of siliceous ooze, but we do see the disappearance of the calcareous ooze at high enough latitude. Okay. So now let's look at the sorting of neritic sediments. So we're going to get rid of the distribution here. And let's look at sediments on the North American Atlantic margin. So it takes a little while for this data set to load. Let's zoom in a little Okay. I'm going to zoom in. So here we see each of these locations is a data point. And at these different data points, the amount of gravel, the amount of sand, the amount of mud, the amount of clay in a percentage was measured. Okay? And so now we're going to graph. And so we know that the sorting means larger sediments are located closer to the coast, and we get progressively finer and finer sediment as we move away from the coast. So we expect a lot of gravel near the coast, and as we go away, we expect more it's a transition from gravel to sand to mud, and then finally to clay. But we don't have distance from the coast as a variable, but what we do have is water depth. And if we assume that the water increases with depth away from the coastline, then we can use water depth as a proxy for distance from the coastline. So let's look at how the percent of the seafloor sediments that are gravel changes with water depth, or with distance away from the seafloor. So here we have the percentage of seafloor sediments that are gravel, so that ranges between 0 and 100%. And on the x-axis here we have water depth, okay, from 0, that's 0 depth, to very large depths, way out here. You can see whenever I put my cursor over a data point in the graph, it's highlighted on the map. You can see that. So you can see a lot of these regions that have high gravel concentrations are near the coast. Right? And as you move further from the coast, you see that the amount of gravel decreases, right? Which makes sense because we expect these larger particles of sediment to settle out onto the seafloor quickly and not be transported far out to sea. Though remember, there are disruptions to the sediment, so we can find larger particles of sediment further from the coast. Maybe they were deposited there at the peak of the last ice age. So for example, this one right here, this is a bit anomalous, where we have this large percentage of gravel pretty far out to sea, way out here. But in general, you see this pretty rapid decline in the amount of, in the percentage of the sediment that is gravel as you go to these deeper waters. Okay, so we find more and more larger percentage of the sediment is gravel closer to the shore. So now let's look at sand. Sand. Now we expect to see somewhat kind of a similar behavior. More sand closer to the coast, and as we move away from the coast, less and less sand. It's not as drastic because sand can be transported more easily than gravel, but we do see that general trend that we have much higher percentages of the sediment are sand near the coast at shallow water depths. And as you move from the coast out to the deep sea floor, you have a smaller percentage of the sediments that are sand. Okay, why? Because the sand settles out quickly and is deposited closer to the coastline, and it's not transported very far out to sea. So you see, it's not as drastic. We find more sand further from the coast than we do gravel, because sand can be transported further from the gravel because it's smaller in size, so it settles more slowly. And because it settles more slowly, it's able to be transported further before settling. Now, if we look at even smaller particles of sediment, say mud, we should actually see the opposite relationship. The amount of the percentage of the sediment that's mud should increase with water depth or distance away from the seafloor. And in fact, we see that. So you see, there's a wide range near the coast, but you see in general that the amount of mud, that the percentage of the sediments in the seafloor that's mud, generally increases with distance away from the coast. So out here, these large water depths, we have very large percentage of the seafloor sediments that are mud. So we see this general trend. Remember, there's disruptions to the to the sorting. And now, whenever we say these relationships, like there's more mud further from shore than closer to shore, those are the trends, right? It's never a hard truth or a hard relationship. So there is some deep sea floors that have very low amounts of mud, and there are some further far from the coast. There are some locations close to the coast that have large amounts of mud. But you can see this general trend that there is more mud the further away from the coast you go. Or a larger percentage of the sediment is mud the further from the coast you go. And finally, let's look at clays. So we should see some relationship where the further you go from coastline, in other words, the deeper the water you're in, the higher the percentage of the sediments are clays. And that is what we see. So there's clearly a sorting here, right? Larger sediments like gravel and sand are preferentially deposited closer to the coastline, where smaller sediment particles like clay and mud are deposited further from the coastline. This is because, once again, the smaller particles have a smaller settling velocity, so they're able to be transported further from land before they are deposited. Just for fun, we can look at other data that was collected. Say, for example, we can look at percent organic carbon. So this would be not calcium carbonate, but actual organic tissue. So that's organic molecules. And you see we find it a lot of it close to the coastline, but not very far from the coast. In the deep sea floor, there's not a lot of organic tissue because most of it, that life is consumed by other organisms in the upper parts of the ocean, or decomposes. So we see that trend, the amount of organic carbon. So that's not calcium carbonate. It's not calcareous ooze. That's inorganic carbon because it's not an organic molecule. Okay. And finally, we're going to look at some photos of the deep sea floor. We'll actually look at some photos of some submarine canyons. And hopefully they come up. Sometimes there's issues with the photos loading. So let's see what happens. Okay, so let's zoom in on these photos. Let's see what we can see. So these are photos taken along in the Submarine Canyon here. And if I click on one, hopefully it comes up. All right, there it is. Okay, so these are taken by a submersible. And let me make this a little bit smaller. You can see that we're fairly far from the coastlines. This is on the continental slope, so we have kind of fine sediment, right? Very fine sediment. And these little round things, those are those phosphorite nodules that are growing on the sea floor. Those are hydrogenous sediment. As we move along to different photos, you see we move along this transect, you can see, the sea floor is pretty much looks the same, right? With this very fine sediment. It's probably terragenous because this is on the continental margin. And we have those phosphorite nodules, which is hydrogenous. So not much, on a few fishes here, there. Okay, but let's go to, say, the other end of the canyon. What's it look like over there? Well, pretty much the same thing. Right. What about deeper parts of the canyon? So most of the seafloor has the same type of sediment deposition as very fine terrigenous sediment, these hydrogenous nodules. Okay. So let's look at a different. Oh, actually, one second. I think let's look at this far end. Let's see what this looks like. Are they going to come up now? Did I lose them? Well, let's look at a different submarine canyon. So where are these? Let's see where these are plotted. They come up. Oh, they're up there. Okay, so let's zoom in up here. Let's look at this canyon. All right. Ooh. So I have a little bit of red light here, but it looks the same, similar to there, except we don't see as many phosphorite nodules. Oh, there's some interesting stuff there. See, it looks like a crab, maybe. We see some. So this could be exposed bedrock, or potentially larger pieces of sediment. This is a submarine canyon, so this could just be bedrock. It's exposed from turbidity currents carving this canyon. And so yeah, I'm not sure if that's bedrock or larger particles of sediment. So here, this could be bedrock or a large boulder. If that's a large boulder, it's an example of disruption and sorting. But it's interesting. There's another large. This is probably bedrock right here. So this is just an exposed cliff of the seafloor because this is a canyon. It's interesting to see these photos of the seafloor. It's not something you see very often. Yes, this is all bedrock. This isn't sediment. So these are sheer cliffs. Piece of sea lettuce or in there, algae. These are sea cliffs in this canyon. Some sheer cliffs we're seeing. Nice crack in there. Okay. See some marine organism growing on that rock. Alright, we're back to a sedimented area, very fine sediment. And you go to the other end. Let's see if by chance, sometimes this works, you can look at some of these photos. Sometimes they don't work, they don't show up. Yeah, I don't know if they're showing up. So let's try one more. And if not, . Oh, here we go. All right. So you can see different images of the sea floor, different locations. So you see this is near the ridge. So there's very few sediment here, very little sediment. We can actually see the exposed bedrock. If we move, we're still at the ridge. See, it's the exposed bedrock. Okay, these are all in the ridge. Let's go right here. Let's see what we see here. Oh, see, now we're on the deeper sea floor, and we see this fine sediment. This is probably biogenous sediment here. And if we go over here, closer to the North American continent, we find, oh look, we find coarse sediment. We see some shell fragments, some evidence of shallow marine organisms. A little further away, it gets finer as we get further from the coastline. Oh, that's trash all the way out there in the ocean. There's some more very finer sediment. If we look in the, say, the Pacific, what does it look like out here? Oh wow, isn't that interesting? I'm actually not quite sure what that is. I'm exploring just as you are. But I don't know if that's an imprint from an organism in the sediment, or if that is an organism itself buried in the sediment. Not sure, or that could be the skeletal remains of an organism that settled to the sea floor. So all different types of stuff. Looks like it might be a piece of trash out here in the middle of the ocean. So lets you know how pervasive pollution is. There's an organism, deep sea organism, a benthic creature on the seafloor. Oh, that's a structure made, I believe, maybe it's like deep sea worms that can tunnel through sediments. You see, anywhere we're in deep ocean floor, we have these very fine-grained biogenous sediments. But if we go closer, still will be fine-grained here. But if we go closer to the continents, we get coarser sediments. Okay, so you can see these. There's a lot more life as well on the seafloor. So I hope you enjoyed this tour of ocean sediments in this edition of GeoMapApp Tours, and I look forward to our next time together. Thank you.